So we left off from question 2.4, where we were looking for the IUPAC name of compound F. So I'm going to just copy this, write it down so that we look at it properly in the whiteboard screen. Okay. So I'm going to copy down the structural formula for compound F. So we had 1, 2, 3, 4, 5, 1, 2, 5, 6, 1, 2, 5, 7 carbons with an H. Every carbon, all these carbons over here were attached to hydrogen atoms. So is this one. So is this one. Let me check again. It's over here, bromine, hydrogen, hydrogen atom, and hydrogen atom. So what we are looking for is the IUPAC name for this compound. So first, what we have to do is to identify what's known as the functional group, which is in what group this molecule with these many carbons belongs to. So we can see from here that we don't have any other types of bonds except for single bonds. And previously we have counted the number of carbons. So we can count them again. We have 1, 2, 3, 4, 5, 6 carbons if we consider this as our parent chain. But if we consider starting from here as our parent chain, we have 1, 2, 3, 4, 5, 6, 7 carbon atoms. So our parent chain will have the hept prefix. And we have also identified that there's only one type of bond here. There's nothing very special about this molecule. And that's only the single bond. So if we have a compound or molecule with single bonds and carbons in its chain, we know that the functional group that it belongs to is that it belongs to the alkane functional group. But we can also note that this molecule has substituents. In the places where we would expect to see hydrogens over here, we have these bromide atoms, or bromine atoms. We will have to determine which positions these bromine atoms are. We can also note that since our carbon chain goes from here and turns and goes in that direction, this carbon atom with these 3 hydrogen atoms attached to it is also a substituent. And because it's a carbon atom with hydrogen atoms where there's only single bonds between them, we know that it belongs to the alkane group. So this is a substituent that belongs in the alkane group, and it has 1 carbon atom. And we know that one carbon atom in the alkane group is a methane. But since it's a methane substituent, which means it is attached to something else that's bigger than it. So substituent, it will be a methyl. So now we have to determine the positions, the numbers, position numbers these substituents are in. So if we count our parent chain, our parent positions or our carbon positions, and label this as position 1, position 2, position 3, position 4, position 5, position 6, and position 7. There's nothing wrong with doing that, counting our main chain starting from here. But you want your substituents to have the highest number possible if we don't have a special functional group, like having some kind of double bond O somewhere here. We don't have any type of special group. It's only an alkane. So we want to prioritize the positions of the substituents. So that means that instead of counting our family or our parent chain from position 1 starting here, our position 1 can start here. So we have our position being 1 here, 2 here, 3 here, 4 here. We have our 5th carbon atom. This carbon atom will be the 6th, and this one will be the 7th. And so we have our bromide atoms or substituents in positions 2 and position 3. And we have our methane attached to the 5th carbon. So it's a methyl substituent in position 5. So now we have to combine all of this information into this IUPAC name. So we have established that this is a carbon chain of 4 carbon atoms, hence the hept, and it belongs into the alkane functional group. So our parent chain is a heptane. And now we note our substituents. So we have a substituent in position 2. We have a substituent in position 3. We separate those positions in a comma. And since we don't have just one bromine atom, we have 2 bromine atoms. When we attach it to the IUPAC name, it will be a dibromo. And then in position 5, we have this carbon atom. We have this methyl substituent over here, which will be a 5-methyl substituent. Now we have to combine all of this into one single name. So if you like, you can put these as 2,3-dibromo. You separate it with a dash, 5-methyl heptane as the IUPAC name for this compound, or it could be a 5-methyl 2,3-dibromo dibromoheptane. So when you read this IUPAC name, you read it as there are 4 carbon atoms in the parent chain, and they belong in the alkane group because there's only single bonds in the carbon chain. There is a methyl substituent in the 5th carbon of this parent chain, and there are 2 bromo, hence the di in the dibromo. These bromanes, one of it is in position 2, is in the 2nd carbon, and the other one is in the 3rd carbon. So that is how the IUPAC name for compound F would be. So is there any question about that? If there isn't, I'll just move on. If there is, you can type it in chat and I'll read it later. Okay, so the next question, which was question 2.4.2, was asking for a balanced equation using molecular formulae for the complete combustion of compound A. So what is this combustion they're talking about? Well, combustion is basically when a substance reacts with oxygen and then they release heat, and if I'm not mistaken, water is also produced. So what we are looking at here is the reaction of, oh my goodness, is the reaction of the compound A with oxygen to produce water, and it also produces an oxide. That's combustion. So written that down. Okay, that's 0.4.2. It's asking for the combustion of this let's go back again and see what's happening. CH3, CH2, CH3, CH2. CH3, CH2, CH2, CH3. So now when we write the molecular formula of this, we count the number of carbons that we have here. We have 4 carbons, so it's C4. And we count the number of hydrogens we have here. We have 3 hydrogens here, plus these 3 hydrogens here, plus these 2 hydrogens here, plus these 2 hydrogens here, which is equals to 10, because 3 plus 3 is 6, plus 2 is 8, plus 2 is 10. So its molecular formula is C4H10. When it combusts, it combines with oxygen, and then it releases heat, and it produces water, as well as an oxide. So what type of oxide would we have here if we form water? There's a carbon here, and we need an oxide that has carbon. Well, in this case, our oxide is carbon dioxide, which is CO2. So what happens is that this, which is ethane, combines with this oxygen, gives us water and carbon dioxide. But this is not a balanced equation. So now we have to balance it. So balancing an equation means that we have to have the same number of atoms in the reactant side to be the same number of atoms in the product side. So on our left-hand side here, which is this one, the reactants, we have 4 carbon atoms. We have 10 hydrogen atoms. We have 2 oxygen atoms. And on our products, we only have 2 hydrogens. We have 1 oxygen here, and we have 2 oxygen here, and we have 3 oxygens. So now we have to balance this. Well, we can try to say, okay, since there's 4 carbons here, we can put a 4 here. But once we put a 4 here, we'll have 4 carbons and 4 carbons, that's balanced. But then we'll have 4 times 2 oxygens, which is 8, plus this oxygen, which gives us 9 oxygen. But here we only have 2 oxygens. So 4 wouldn't be an appropriate one, because now we have to balance the total here. Another thing, we can look at these hydrogens. We have 10 hydrogens here, we have 2 hydrogens here. Since we have these 2 hydrogens, maybe we can put a 5 here, so that we have 10 hydrogens here, and we have 10 hydrogens here. But what happens is that now we have 5 oxygen plus 2 oxygen, which is 7 oxygen, and we're still left with 2 oxygen over here. So our 5 doesn't fit. Since we have here, we have an odd number of oxygens. We have 3 oxygens here, and we have 2 oxygens here. We can try to make it have 6 oxygens maybe, If we have 6 oxygens here, where we put a 3, we can put a 4 over here. So now we have our oxygens are balanced, but our hydrogens are not balanced. So we can multiply this 2 by 4 by 2. So we have 4 here. And instead of having 3 oxygens here, we try to have 6 oxygens. Okay, that's a plus. Okay, let me erase this here. And we also have to think about these hydrogens over here. We have 10 hydrogens here. We have 2 hydrogens here. So since hydrogens also are at this biggest number here, we can try to deal with that. If we have 10 hydrogens over in our left-hand side, and we have 2 hydrogens in our right-hand side, if we want to make them equal, we can multiply this 10 by 2, and multiply this 2 by 10, so that we have 20 hydrogens in each side. So we multiply 2 here, so we have 20 hydrogens. In order for us to get 20 hydrogens, we can multiply with the 10. So now we will have 10 oxygens and 2 oxygens over here, which gives us a 12. And we only have 2 oxygens here. If we want to have 12 oxygens, then we can multiply with a 6 maybe. So now we have 12 oxygens and 12 oxygens. But the carbons we have are not the same. Here we have 8 carbons, which is this 2 times 4. But here we still have only 1 carbon. So now we deal with that carbon and say, okay, how about we put an 8 over here? So now we have 8 carbons, we have 8 carbons, we have 20 hydrogen atoms, and we also have 20 hydrogen atoms. Now we're left dealing with the oxygen atoms. We have 10 oxygen atoms on this side, and we have 16 oxygen atoms, which gives us 26 oxygen atoms. But here we have 2 hydrogen atoms. So to balance this, we can multiply it by 13, because 2 times 13 gives us a 26. So if we have a 13 here, now we have 26 oxygens on this side, and we also have 26 oxygens on the other side. The number of carbons. So we have our carbons, we have our 8 carbons. We have our hydrogens, we have our 20 hydrogens. And we have our oxygens, there's 26 of them. Let's check on the right-hand side. Hydrogens, we also have 20. Oxygens, we have the 10 plus the 16, which gives us 26. And then the carbons, we have 8 carbons. So our balanced equation would be C4H10 plus O2 O2 H2O plus CO2. Our balanced equation would be this. So is there any question about this one? If everyone is clear, then we can move on. If there's a question, you can type in chat. Okay. That concludes our question 2. So now we move on. We move on to question 3. Okay, question 3 states that there's 3 compounds that are used to investigate one of the factors that influences boiling point. the results obtained are shown in the table below. So we have 3 compounds here. We have butane, we have propan 1-ol, we have ethanoic acid. We have the molecular masses, which are written here, and we have our boiling points, which are written here. So if we want, we can note what's happening with these compounds. So we have our butane, which is an alkane. We have a propan 1-ol, which is an alcohol, and we have this ethanoic acid over here, which is an ester. So we have 3 different compounds. 3.1 asks us, it says, in one investigation, the boiling points of compound B and compound C are compared. Then we are asked, is this a fair investigation? Write down yes or no. Then you refer to the data in the table and give a reason for your answer. So what is happening with compound B? Compound B is this alcohol, has the same molecular mass as compound C. It has this boiling point of 98 degrees Celsius. Compound C, this ethanoic acid over here, also has molecular mass of 60, and it has this boiling point. So now it asks us, is this fair to compare these 2 compounds? Yes or no? Our answer is yes. Why would we say yes? It's because we are comparing 2 different compounds that are the same mass or the same molecular mass. That is why this comparison between the 2 compounds would be the same. And then 3.1.2 asks us to write down the independent variable for the investigation. So what would be the independent variable? The independent variable is the variable that we can't change. If we look at the molecular mass, for example, we could change the molecular mass. You could change how much of butane you use, or propan 1-ol or ethanoic acid you use for this experiment. But you can't change the boiling point, because the boiling point depends on this compound. But the compounds, we can't change the compounds as well. The compounds are as they are. So our independent variable for this investigation would be the compound types, or the types of compounds, or maybe the functional groups of the compounds. What we are investigating over here is the boiling point. So we can't use it as the variable that we can't change. This boiling point is dependent on the compound, but the compounds aren't dependent on anything to be themselves. So that is why they would be the independent variables for the investigation. And then 3.2 asks us, which one of the following compounds, A, B, and C, has the highest vapor pressure? Now, what is vapor pressure? So the definition of vapor pressure, or actually the definition of the boiling point, since it's the thing we're investigating here, is that it's that temperature where the vapor pressure and the atmospheric pressure are the same. But how do we determine what would have the highest vapor pressure or the lowest vapor pressure? So the vapor pressure is determined by the boiling point. If you have a low boiling point, it means that between your atoms, you have weak intermolecular forces. So if you have weak intermolecular forces, we won't need that much energy to be able to break you apart. So that would mean that your boiling point would be low and your vapor pressure would be high. So then we look at the table and look for what would have a low boiling point. and that would be the compound with the high vapor pressure. So here we have our butane, which has a boiling point of 0.5 degrees below zero. So the answer for 3.2 would be butane. And why would it be butane? It's because it has a low boiling point, which means that it has a high vapor pressure. And then 3.3 asks us to refer to the intermolecular forces present in each compound and fully explain the trend in the boiling points as shown in the table above. So what's happening in this table? We have these three compounds that almost all of them are the same molecular mass. And the boiling points, as you go down the table, they go from negative 0.5 degrees Celsius, then it says 98 degrees Celsius, then it says 118 degrees Celsius. So the trend that's happening here is that as you go from A to B to C, the boiling point is increasing. So what's happening? Why is it happening? Firstly, we've just talked about butane, and we've talked about the intermolecular forces that are present in butane. But how do we know that butane has weak intermolecular forces? Well, butane belongs into the alkane group. And we know that in the alkane group, the carbon atoms are bonded to each other in single bonds. And those single bonds are the London forces. Those forces are quite weak if we are going to compare them to propan-1-ol, which is an alcohol, where there is an oxygen atom. So if we write that down, we write the functional group of an alcohol. So we have our butane, we have our propan-1-ol, and we have our ethanoic acid. Butane, that means there's 4 carbon atoms, and it's in the alkane group. So all of those carbon atoms are combined with hydrogen atoms. But between those carbon atoms, there are only single bonds. And these single bonds are weak if we're going to compare them to propan-1-ol. Propan-1-ol has 3 carbon atoms because of the prop, but it is an alcohol. So there's a hydroxide group over here, OH. I have an H here, H, hydrogen atom, another hydrogen atom, and a hydrogen atom. If we compare these two molecules, carbon atoms bonded to hydrogen atoms or carbon atoms bonded to carbon atoms are weak in comparison to a carbon atom bonded with an oxygen atom. So as we go from here, from the butane to the propan-1-ol, the strength of the intermolecular forces increases. And what about with ethanoic acid? Well, ethanoic acid has 2 carbon atoms, but there's a double bond O. A double bond is much stronger than a single bond. So as we go from the propanol to the ethanoic acid, the strength of the intermolecular forces also increases. So what this means is that the boiling point will go from low, let's go from higher, and this one will be the highest. And so our question was asking us to explain the trend in the boiling points. So if we are to explain the trend as we go from butane to propanol, to ethanoic acid, the strength of the intermolecular forces increases. If we want to go into detail, we can talk about how there are only single bonds in the carbon atom, in the butane within the carbon atoms, where here we have a carbon atom that is attached to an oxygen, but there's only a single bond as well. But this bond is stronger than this one. And we also have a carbon atom bonded with an oxygen atom, but there is a double bond as compared to a single bond here over here. So the trend is intermolecular forces are becoming stronger as you go from one compound down the table. Therefore, the boiling points increase. What this means with regards to the vapor pressure is that the vapor pressure decreases also as you go from compound A to compound B to compound C. So that would be our answer for 3.3. And then 3.4 asks us, which compound, butane 1-ol or propan 1-ol, has the higher boiling point? Give a reason for your answer. Well, butane, Question is asking us to compare butane 1-ol and propan 1-ol. So there are similarities between these two compounds or two molecules. They're both alcohols, but there's a difference. If we can first write down the structural formulas for both of these compounds and to see this difference. Because this one is a butane, we know that butane indicates that there is in the longest chain there are 4 carbon atoms. Propan says that in the longest chain we have 3 carbon atoms, and it's an alcohol in the first carbon, alcohol in the first carbon as well, and the rest are hydrogen atoms. The same with the propan 1-ol as well, have the hydrogen atoms around all of the other carbons in the main chain or the parent chain. Now the difference between these two molecules is that butane 1-ol has a longer carbon chain than propan 1-ol. So if a molecule has a longer carbon chain than this one, what this means is that it has more intermolecular forces inside it compared to this one. Since there are more intermolecular forces, there are stronger intermolecular forces because the chain is longer compared to that of propan 1-ol. And because butane 1-ol has a longer carbon chain than propan 1-ol, it would have a higher boiling point than propan 1-ol. So if you have a higher boiling point, higher BP, you have a lower vapor pressure. So since this one has a lower boiling point compared to butane 1-ol, it would have a higher vapor pressure. And our question was asking us, which compound has the higher boiling point? It would be butane 1-ol because it has a longer carbon chain than propan 1-ol. So for question 4, we have polymerization. It has to do with polymers, plastics and all of that. So here we have a balanced equation that is showing a polymerization reaction, and we are asked in 4.1.1 to state the type of polymerization reaction represented by the equation. 4.1.2 asks us to give the IUPAC name of the monomer, and 4.1.3 asks us to give the IUPAC name for the polymer. Okay. So what is this type of polymerization that they're talking about here? It's known as addition polymerization. Why? Because here we have this compound with the double bond reacts with something, or something happens to it, and it becomes a single bond polymer. Addition polymerization, or a polymer, an addition polymer, it's a chemical reaction where two molecules form a larger molecule that repeats the structural unit. Here, our structural unit is a C2 and H4. If the C2H4 here, it's repeating, as you can see with the subscript N here. The type of polymerization reaction represented by the equation above, this is known as addition polymerization. And then 4.1.2 asks us to give the IUPAC name of the monomer. So what is this monomer that they're talking about? Monomers are the basic units or the building blocks of polymers or building blocks of proteins. So what is this building block that they have here? This is a building block. It's on our left-hand side. It's a C4, it's a C2H4 with a double bond. And we know that if there's two double bonds, if there's a double bond between carbon atoms, then the functional group that molecule belongs to will be an alkene. So the IUPAC name of the monomer here will be an ethene. Why is it an ethene? It's because there is two carbon atoms, there's a double bond between them, 4 hydrogen atoms attached to those carbon atoms. So our answer for 4.1.2, sorry, 4.1.2 is ethene. This is the monomer. Four point 1.3 asks us, okay. Then 4.1.3 asks us to give the IUPAC name for the polymer. So the polymer is just, we have just stated above that the monomer is the building blocks of a polymer. So many monomers make up a polymer. So the IUPAC name of our polymer would be a polyethene, because there's many ethenes making up a polymer. So the IUPAC name would be polyethene. Many ethenes making up the polymer. Question 4.2 asks us, okay, goes as follows, reads as follows. Propan 1-ol undergoes two different reactions as shown in the diagram below. So we have our propan 1-ol. There is one reaction where there's hydrochloric acid involved, and it results in compound Y. There's reaction 2, where there is concentrated sulfuric acid, that H2SO4, it gives compound X. This compound X undergoes a reaction with water. There's also concentrated sulfuric acid involved in the reaction, and it gives us this major product in compound Z. So we are asked to write down the following. So 4.2.1 asks us to write down the type of reaction represented by reaction 2. 4.2.2 asks us to write down the function of the concentrated H2SO4 in reaction 2. 4.2.3 asks us to write the IUPAC name of compound X. 4.2.4, the structural formula for compound Y. 4.2.5, type of reaction represented by reaction 3. 4.2.6 wants us to write down the IUPAC name for compound Z. So the first question is asking us to write down the type of reaction represented by reaction 2. So what's happening in reaction 2? We have propan-1-ol. There's concentrated sulfuric acid involved, and it gives compound X. So what happens when an alcohol, which is the propan-1-ol, undergoes this reaction? Where one of the products is going to be water here in compound X. So this type of reaction is known as a dehydration reaction. A dehydration reaction is a reaction where one of the products is water. What happens is that there's an alcohol that combines with a type of acid to give us this water and some compound X. And then 4.2.2 asks us, so what is this function of this concentrated sulfuric acid that's in reaction 2? The sulfuric acid that's here, it acts as a catalyst. A catalyst is a substance that speeds up a reaction. What it does is that it removes these water molecules, and then it serves as a dehydrating agent, which is why in one of the products we will get here, we get the water. And then 4.2.3 asks us to come up with the IUPAC name for compound X. So we'll switch to our whiteboard. We have propan-1-ol. That's our 4.2.3, I think. Propan-1-ol. So we can write down the structural formula for propan-1-ol so that we can see how the molecular formula looks like. So it's an alcohol. There's a hydroxide attached to the first carbon because of this one. And because we have propan, it means that the carbon chain has 3 carbons. So propan-1-ol will look like this. We have our hydroxide, or hydroxyl group on the first carbon, hence the 1, and we have 3 carbon atoms. So the rest of the carbon atoms will be attached to this hydrogen, 2 hydrogen atoms. And then what happens is that since we have stated that the reaction that occurs in that reaction 2 is a dehydration, and we know that one of the products is water. First, before we can look at that properly, let's write down the molecular formula for this, which is, we count the number of carbons we have here. We have 3 carbon atoms. We have 1, 2, 3, 4, 5, 6, 7, 8 hydrogen atoms, and we have 1 oxygen atom. So that propan-1-ol undergoes something. Undergoes dehydration, and then we get water plus something else. So if we eliminate water from here, which is taking H2O, so we remove the H2O from here, that's removing 2 hydrogen atoms and removing the oxygen. We are left with C3 because we didn't do anything with the C. And since we removed just 2 hydrogen atoms, we are left with 6 hydrogen atoms. We've also removed the O because it was attached to 2 hydrogens, the H2O over here. And this is what we left with as our product X. Was it product X? Compound X. Our compound X. So what is the IUPAC name of this compound X? We have its molecular name here. So we have these 3 carbon atoms. We have 1, 2, 3 carbon atoms. But we have 6 hydrogen atoms. Can attach 1, 2, 3, 4, 5, 6 hydrogen atoms. So what's happening over here? You know that at least one of these hydrogen atoms should be complete with 4 hydrogens, with 3 hydrogens, because there's supposed to be 4 bonds surrounding a carbon atom. We have 1 hydrogen here. We have 1, 2, 3, 4. We have 5. We have 6. So what this means is that over here, somewhere here, we have a double bond. We're supposed to have 1, 2, 3, 4, 5, 6 hydrogen atoms. I think I did them correctly. Okay. Okay, no, it's supposed to be double bond. And we count. There's 1, 2, 3, 4 bonds. Over here, we move this one.